Okay, so today we'll talk about homology. So homology of sheaves, and well, following Grothendieck, we'll define homology as the derived functor of global sections. So in order to do this, we need to have an abelian category of sheaves, and we have to define the functor of global sections, and we have to prove that the category of sheaves, say of abelian groups, has some nice properties. For example, it has sufficiently many injective objects. So let's see how it works. So first, I will explain a general theory. It will not be long. Okay. So suppose we have a site. We have the category of presheaves, just contravariant functors. And this time we'll talk about, well, for example, presheaves of abelian groups. And I will shortcut this notation. This will be just see. This is a, it has a subcategory, sheaves. And so this functor has, so general lemma is that this functor has left adjoint. Lemma, this has left adjoint, which is called sheafification. So F goes to F sharp. That will be the name for the sheafification. So let me explain a construction of the adjoint functor, sheafification. So construction of F sharp. Well, so as in classical topology, you do it in two steps. So a sheaf is a presheaf with two properties. First of all, any section which is locally 0 must be 0. And secondly, you can glue sections. So if you have locally given sections, it should give rise to a unique global section. So and sheafification consists of two it's constructed in two steps. First, you start with a presheaf and you make it separated. Namely, a presheaf is called separated if any section which is locally 0 is globally 0. And then you apply essentially the same construction once again, and you get from a separated presheaf a sheaf. So this is how it works for sites. So we define a functor that's called epsilon from presheaves on C to itself. If I have a presheaf and I have an object of C, I will define So the value of this epsilon of f at x is the colimit of locally given sections of f. So where colimit is taken over all covering sieves on x. Okay? So you may think that if you start with a pre-sheaf and employ this procedure, you already get a sheaf. But this is false.
If you had a topological space,
yes.
that covering sieves are exactly in bijection with open covers?
No. No. For example, if you have an open cover, you can get a suppose you have you can cover x by u1 and u2, maybe. But you can also write it as u1 union u2 union u1 intersected u2. The sieves generated by these two covers are the same. But covers are different.
There are no more sieves than there are open. I'm concerned that you just, jumped 2 degrees of largeness in this one definition.
Well, so we have a notion of a cover, right? So by definition, a site is a category with a class of sieves which we call covering sieves. For any set of objects over X, we can define a sieve generated by this family of objects, and we say that a family of objects cover X if the generated sieve is a covering. So this procedure of generating a sieve from a cover identifies some covers, right? For example, the sieves generated by this open sets is the same as the sieve generated by this, because this guy maps to U1, so it must be in the sieve generated by this cover.
So my problem is that if X is a topological space, open subsets form a set, and any covering sieve is generated by a subset of set of all open subsets. So there is a set of covering sieves. But in general, it's not. Or really demanded, there is a set of covering sieves.
Let's demand this. You mean your problem is that it's it might be too large. Let's ignore this. So there are some words people usually say, but I don't know if this causes any real problems. So yeah, maybe you need to require that covering sieves form a set. But
can we classify similarly covering sieves on an Intel site, which we care about? That there is some set of covers such that any sieve is generated by a subset of these covers.
well, probably not. But can you classify them for the risky topology or classical topology? What do you mean?
Yeah, in the classical topology, you had a set of all open subsets, and any sieve was generated by a subset of this set.
And in Ital topology, you have a collection. A collection means a set for me of Ital schemes over X, whose images cover X, and let's generate all covering sieves.
It's probably not. Well, I still can't figure out why this can be replaced by a set, but
Okay, so now a lemma, which is that if for any pressure f, epsilon of f is separated. And separatedness means that f of x epsilon of f of x maps injectively to epsilon f of u for any covering sieve. For any covering sieve. Yeah. And the second assertion is that if you apply this functor twice, if f is separated, then epsilon of f is a sheaf. With this said, the proof does not repeats this classical argument. There is no difference. So, having this lemma, we define sheafification as epsilon of f. And again, if you work just with topological spaces, you still need to apply epsilon twice. Okay, so proof is omitted. So some proofs will be left as an exercise, but this, I think, does not really deserve to be called an exercise. Or, well, proof is omitted. In fact, today there will be only one exercise, which is. Well, first you make your pressure separated, apply an epsilon once, and then you again.
So this is a tricky step, which is both steps. It's not.
Say it again.
But you do the same step twice, and it's
yes, yes. Okay, so. No.
This epsilon does not have an inversion.
Yes. Давайте я попробую в следующий раз придумать. Я забыл. Ну, проблема понятна какая. Вы пытаетесь проверить, что вот это вот пучок. Ну, как вы это делаете? Ну вот вы даже вот покрываете, давайте посмотрим такой пример. Вот вы x покрываете двумя открытыми множествами, u1 и u2. И вам надо доказать, что, значит, сечение на u1 и на U2, и что если у вас есть пара сечений на U1 и на U2, которые на пересечении совпадают, то тогда вы можете построить единственным образом сечение на X. Но если у меня есть сечение на U1 и на U2, которые на самом деле сечение ну вот у меня есть, вот я сначала беру f, а потом беру эпсилон от f. Если бы у меня были сечения самого f на U1 и U2, которые на пересечении совпадали, то тогда, конечно, это определяет сечение эпсилон от f. Но проблема в том, что когда я эту процедуру применяю, то у меня уже вот здесь становится больше сечений. И условие, что они совпадают, ну вот, и как бы непонятно, как уже делать даже вот в этом случае. Проблема возникает. Вот. Я приведу какой-нибудь пример. Хорошо. Значит, very good. So we'll need this in slightly more general setting. So let's assume that well, sometimes you have to work with not all sheaves of abelian groups, but say sheaves of vector spaces, or sheaves of modules over a ring, or more generally, sheaves of modules over some given sheaf on C. So let O be be a sheaf of rings on C. Think of O, for example, think of C as scheme X equipped with Zariski topology and O the structure sheaf. So we can talk about sheaf of O modules. So we have we have the category of presheaves on C of modules, and here I have sheaves of sheaves of modules. And again, this embedding here admits left adjoint. So this is left adjoint. Adjoint. And the formula for this left adjoint is the same formula. So you also prove it using this functor epsilon. In fact, the sheafification commutes with the forgetful functor from the category of sheaves of O modules to the category of sheaves of abelian groups. So if you have a presheaf of O modules, you apply this left adjoint functor and then forget O module structure, you get just the sheafification of the presheaf of abelian groups obtained by forgetting a module structure here. Okay? So that's not, this is one nice thing. And this has a corollary. Another lemma. So all this category for any O is an abelian category. So this is a structure of a category, right? So in order to check that a category is abelian, you have to show that there is a final object, which is also initial object, which is just zero sheaf, that there are finite direct sums, that the map from finite direct sum to finite direct product is an isomorphism. And also you have to check the existence of kernels and co-kernels, and show one last axiom that the two ways to define image of a morphism, the image and the co-image, is the map from co-image to image is an isomorphism. So I will not give a detailed proof. It's boring. So the for example, the co-kernel, how you define the co-kernel? Well, it's not you have to show that a certain functor is representable, right? So again, the existence of a co-kernel is a property of a category. So you need to, but in order to check that a certain functor is representable, it's convenient to have a candidate for the object it represents. So suppose you have two sheaves, and then, so how you define the, well, what will be the co-kernel? I will tell you the answer, right? So the answer is that you take pre-sheaf that takes x to co-kernel of the map from f1 of x to f2 of x, and then this, so this is a, this defines a pre-sheaf, and you take its sheafification. Okay? This is not a definition. This is a statement. Rather, this is a statement that indeed, given a map from this sheaf to any other sheaf is the same as giving a map from F2 to this other sheaf G, such that the composition with this arrow is 0. So, okay. Now, that's not enough for constructing a homology theory. As I said, we need to show, we have to know that this category has sufficiently many injective objects, lemma. So sheaves on any side and any ring side has enough injectives. Well, if you look at the proof, for example, that the category of modules over a ring has enough injectives, and then in my course in algebraic geometry, we proved that the category of Zariski sheaves has enough injectives. So the proof is quite a long series of constructions, right? You construct, for any object, you construct in embedding the injective sheaf, which you may immediately forget after the proof is completed, right? So how you prove that a module has, the category of modules have enough injectives. So you give some rather arbitrary construction. So Grothendieck realized the very beginning of his series of work in 50s, when he just started working in algebraic geometry, that you can single out class of abelian categories that have enough injectives. And in almost all applications, you can just check that this list of properties Grothendieck formulated are satisfied for the category you are interested in. So, so I will just explain this categorical lemma of Grothendieck. So suppose A is an abelian category. So category. And I want to know whether it has enough injectives. So assume that it has the following properties. Well, first of all, assume that A has all direct sums. Infinite direct sums. Secondly, I assume that these direct sums are exact. What does it mean? It means that if you have a collection of well, if you have a short exact sequence, Ci, these are exact, then this sequence is also exact. As exact. And finally, well, not finally. So the third condition is that filtered colimits, for example, directed colimits, are exact.
What's the difference between filtered colimit and directed colimit?
Okay, so what is a filtered category? A filtered category, let me write it here. So is the following. So a directed category is a partially ordered set with certain property. For any two objects, you have a sort of a larger object.
Filtered is the same, but you can have multiple elements.
Right, exactly. But so one of axiom is that if you have two objects and two arrows, then you can find another arrow such that the composition are equal. So it's not too bad. Okay?
If you have two objects, you have a third object.
Yes. So if you have x making two. Да. Направленные не может быть две стрелки. Там это частично порядочное множество. Ну, что? Ну, нет, не всегда. Не всегда.
Любой предел сводится к направленному плюс к уравнителю.
Уравнитель. Нет, уравнитель это как раз это предел, это пример не направленного, не фильтрованной категории.
Его не обязательно точно.
Да. Okay. So let's before I state the last property, so let's discuss what this means. So let's take our favorite category, the category of abelian groups. Then all these properties hold. Let's give an example where, say, the last property does not hold. So, okay, so for abelian groups, direct limits, co-limits, is an exact functor. But it is well known that the inverse limit, just over positive integers, over natural numbers. So it's well known that this, where I is not an exact functor for abelian groups. There is R1, Katya, that you discussed some time ago.
But it is not a co-limit.
It's not a co-limit, it's a limit.
Yeah.
But it becomes a co-limit if you take the opposite category. So, for example, the category opposite to the category of abelian groups has property 1, 2, but not 3. Ну, значит, я вот утверждаю, что неверно, что вот этот функтор не точный. Let's give an example where the second property doesn't hold. To make this example simpler, let's again. So let's kind of the examples that appear in nature is where the direct products is not an exact functor. Opposite category. So, and the example where the direct products is not an exact functor is just the category of sheaves. So the problem is that the stock of direct product of sheaves is not direct product of stocks, right? So you might need to pass for smaller and smaller open. If your sheaves are ugly, then it's easy to convince yourself that it's not this functor of direct product is not right exact, it's only left exact. So for the opposite category, property 2 will not hold. So it's not automatic. And so the last property, which I could have kind of ignored because I do not care about all these set theoretical issues, so I just copy it from textbooks. That A has a generator. Что они?
Да, мы требуем, что filtered limits exist and are exact.
So no, any filtered. So once you have infinite in abelian category, once you have all direct sums, you can express, in fact, any colimit as in terms of infinite direct sums. Yes. Yeah. As a co-kernel of certain map. So so the last property is that A has a generator. So what is a generator? So a generator is an object U such that functor from A to say, abelian groups that takes an object X and sends it to morphisms in my category from U to X, reflects isomorphism. Meaning that if you have a map from X to Y, if the induced map of abelian groups is an isomorphism, then the map from X to Y is an isomorphism. So to play with this a little bit, so let's think of a category of modules over a ring. What is a generator? The ring itself. Consider it as a free module, because then this is just the forgetful functor. So if you consider the category of sheaves, say in a topological space, what would be the generators? Say it again? Is it really true? So are you saying that if you have a map of morphism of sheaves, which is isomorphism on global sections, then it's an isomorphism? Пучки небоскребы. Пучки небоскребы тоже не работает. Не может не быть хомов из пучка небоскреба, например, в постоянный пучок. В частности, это условие означает, что никакой ненулевой объект не переходит в ноль. У пучка может не быть глобальных сечений, поэтому это не есть образующий. Тоже не работает, потому что, еще раз, из пучков небоскребов может не...
Прямая сумма по всем замкнутым множествам ограничений постоянного пучка на это замкнутое множество.
Так, нет, тоже я не понимаю. Мне кажется, что может такое быть. Да, просто возьмите пучок без глобальных, какую-нибудь локальную систему. Какие же там будут?
По всем открытым подмножествам.
Продолжение нулем. Значит, вот функтор, который f переводит в f от u, он представим. А именно f от u равняется морфизмам из постоянного пучка. Здесь J написано. J — это вложение. В f. Потому что этот функтор, он правый сопряженный к ограничению, а ограничение — это как раз, значит, надо f ограничить на u и взять потом глобальное сечение. Получится f от u. Но мы знаем, что вот все вот эти вот функторы, вот если я рассмотрю вот прямо функторы из категории пучков в такую прямую сумму категории Абелевых групп, занумерованных всеми открытыми множествами. Этот функтор, безусловно, будет, ну, в общем, консервативный. So this implies that so if you take the direct sum of z of all these guys, j, that's u chic of z over all u in X is a generator. Okay? So that's how you, so this is the, so this is a list of properties in abelian category A. And so fact that if you have a category with all these four properties, then A has enough injectives. Is it equivalent? So you want to say that it's, I think there should be, so there is a theorem of Popescu, which is, for example, in Stack's project. I think that there should be some it's not true as stated. There should be something else, another condition. But so indeed there is a candidate, right? The property is very simple. It should be U should be a projective object. Then it's okay. So if you have a projective generator, then it's equivalent.
But this ring can even be commutative. Like every category with property 4 with projective generators, like it is equivalent to the Abelian category of modules over.
The opposite of endomorphisms.
Yes, but the ring of endomorphisms need not be.
And so what?
Yeah.
Yeah. Yes. Okay. So if you want something to be in equivalence, in particular, a functor has to be exact. So you want this to take for an equivalence, right? So, okay. The proof is formal. So I will not, again, write details, but so what is the idea? So first of all, it's using 4, you can formulate the following criteria of injectivity. So if you have an object X, then in order to check that X is injective, it suffices to verify the following, that for any subobject P of U, any map from P to X extends to a map from U to X. So a priori, one has to check this. So injectivity means that for any inclusion like this, for any U, so any map from P to X extends to a map from a larger object. But again, so if U is a generator, then it's enough to check this for U. And so the idea is that you can take a push out of this diagram. So you can, how it's called? It's U plus X modulo P. So you have. So so you start with X, which does not satisfy this property. And then the idea is that you want to enlarge it. You want to embed X into something bigger, such that the morphism from P to X extends to a morphism from U to this larger object. Of course, this larger object need not be injective, so there might be some map from another subobject of U, say P prime, to this guy, which does not extend to a map from U to this guy. But then you can apply this construction again, and so the injective hull of X is defined as a certain co-limit of over a diagram of these types. Okay, that's Grothendieck deconstruction. And if I ignore theoretical problems, I would just take for U direct sum of all objects, which, however, leads to some unpleasant consequences. Yes, it gives you a factorial hull for any injective object.
But it's true that for even ring like Z of X, Y, there is no explicit example of injective one. So they are all constructed by sort
Yes, yes. Okay. So having all this, we having this lemma. So the proof of the lemma consists of verifying that sheaves of homogeneous on any side satisfy all these four axioms. Now, okay, so I want to now do homological algebra with that category. In particular, I want to define homology as functor of derived functor of global section. So if you have any left exact functor from this category to the category of abelian groups, you can any left exact functor has derived functors. So explicitly, you pick an object, you pick an injective resolution, and you apply your functor term-wise, and then take homology. That's the construction, but derived functors can be, again, characterized by universal property, and this is, you need enough injectives to prove the existence. So sometimes derived functor exists even if you do not have injective objects. Okay, for example, when your functor is exact. That's a good example. So now, what is a global section? Global sections. So how you define it? So we need a functor from category of sheaves on C to category of abelian groups. What is it? What is a global section of a sheaf? How would you define it? If you have a final object, yes. But I don't assume this. It's not an assumption for a Grothendieck for a site. So how should you think of a global section? Что? Very good. So gamma of f is defined as morphisms from constant sheaf. Let me, because I work in this, let me put, since I choose to work in this generality, let me, I will put O here, which I consider as a, so this is a morphism in the category of homogeneous, right? To F. If we worked with the category of sheaves of abelian groups, it would be just Z, right? So what does it mean explicitly? It means that for, so a global section is a collection. For every object of C, you have a section of F on this object. And it's compatible with all restrictions. So these examples were of sites where you don't have final objects appear in nature. For example, crystalline site. There will be in, for example, in Ital site, and also in, say, FPQC site, we have final objects. So global sections, if remark is that if X is a final object, in C, then global sections of F is just F of X. Okay. And so definition now is that so this functor, because it's morphisms in abelian category, right? Morphism is always left exact, so this is a left exact functor, and we can take its right derived. So homology of a site, a sheaf on a site, is defined to be the right derived functorial global sections. Very good. Now, this is formal, so that's unfortunately not. I will need some more general nonsense on sites. Well, not maybe nonsense, but let's discuss some examples first. It's with the definition that I gave, it's hard to visualize elements of the homology groups. What is the geometric meaning of this? And higher homology groups have no geometric meanings, as well as higher derivatives of a function. Only maybe first, and with some effort, second derivative of a function has geometric meaning. The same is true for homology. Let me explain this an interpretation of H1. Okay. So this is very important. So we will interpret elements here as isomorphism classes of some certain object of objects in a certain category, namely in the category of torsors. So let G be a sheaf, and let's for the sake of simplicity now assume a sheaf of abelian groups. Then, so we have notion of a G torsor. I form a category in C. And I claim that this category is equivalent to the category of extensions. Namely, say this is name for my torsor, and so the corresponding extension will be denoted by T tilde, and that's the extension of the constant sheaf Z by this sheaf of abelian groups G. So this is again an equivalence of two groupoids. Discard all nano-isomorphisms. So morphisms between extensions are morphism between short exact sequences, which are identity on G and on Z. The construction is the following. So I will define for you the functor in this direction. So if you have T tilde, then so how you define T? T of any U is pi inverse of T tilde of U. So you have action of G of U on this set, and locally, so if you have any U, it can be covered. You can find the covariant sieve over U such that for any object of the covariant sieve, this T of U is non-zero. So this is either empty or it's has a simple transitive action of G of U. Right? So I claim that this is an equivalence, this functor that I defined for you is an equivalence of categories. Да, какую-то я глупость написал. Спасибо. Единицы просто. Простите, пожалуйста. Да, должен был написать вот это. Да, должен был написать вот это. So the underlying idea here is that so if you have an abelian group, then the category of torsors of an abelian group is the same as the category of extensions of group Z by this abelian group. In the category of extensions, also in the category of abelian groups. So how you check that this is an equivalence of categories? Well, if you consider subcategories where sort of extensions, split extensions, and trivial torsors, then this definitely will be an equivalence. So here you have only one isomorphism class of objects, but really the content is that this functor reduces isomorphism on morphisms, right? Automorphism of the trivial torsor is precisely global sections of G, and automorphism of trivial extension is also global section of G. Right? Because if T tilde is G plus Z, so I look at the upper triangle matrices with one under diagonal. That gives me. And then both kind of the formation of the category of torsors and extensions, the rule that assigns an object the category of torsors over this object in C is a sheaf of categories. That's one way of saying it. This means that it's an equivalence. So in particular, so I recall that let's reformulate this. So we have global functions is homomorphisms, morphism from O to F. And the derived functors are X, right, by definition of X. So in particular, H1 is X1. And in any abelian category, X1 classifies the extensions. So this follows that H1 of X with coefficients in G is isomorphism classes of G torsors. So when G is an abelian group or sheaf of abelian groups, G torsors form a monoidal category. You can take the tensor product of G torsors in the same way as you take the tensor product of line bundles. So the operation, the addition operation here corresponds to the operation I just mentioned on G torsors. In the last lecture, we defined the notion of G torsors for any sheaf of groups, not necessarily abelian. So in this case, we can still talk about isomorphism classes of G torsors, but then this isomorphism classes is merely a set. It's not a group. So it provides a candidate for kind of non-abelian first homology with coefficients in any sheaf of abelian groups. And this has, for example, we proved that if G is GLN, then this is the set of isomorphism classes of vector bundles. Right? So let's give some concrete examples of how it, let's see, let's do some computations. Okay, so in order to do the computation, let's formulate a corollary. Let's derive another corollary of from FPQC descent. So suppose you have, suppose we are given two sheaves, G and F, just quasi-coherent sheaves on a scheme X. Then we have two categories. One is a category of extensions. In the category in, say, 0, F, T tilde, to keep my previous notation, oh, sorry, G, F. In sheaves of modules, Zariski topology, modules over structure sheaf, modules over OX. And another category is a category of extensions, same extensions, G, T tilde, F, in the category of sheaves of all modules on all schemes over X equipped with FPQC topology. Again, I take modules over OX. So here, when I write this, I mean that any quasi-coherent sheaf on X defines a sheaf on this category, right? So if you have a scheme over X, you just pull it back to that scheme. So G can be viewed also as a sheaf of all modules on this category. And now there is a functor in this direction. Well, how this functor works? So maybe, so a remark is that, so if you have an extension like this, then T tilde is automatically quasi-coherent, right? So the category of quasi-coherent sheaves is a subcategory, is a category of all modules, and it's stable under extensions. So T tilde is quasi-coherent, so I can apply the same procedure that I apply to G and F here. If I have any scheme over X, I can put back my T tilde to that scheme and get the functor. And now a corollary of faithfully flat descent is that this functor is in equivalence. Okay? And combining this with, should I comment this, or it's, что? Ну давайте посмотрим. Ну, вот у нас такое есть расширение. Давайте выберем покрытие x, на котором оно тривиально. Решето, покрывающее решето. Значит, для каждого покрывающего решета, это вот расширение такое тривиальное, значит, это мы можем построить, ну, значит, если мое вот, значит, если, опять же, я рассматриваю расщепимые последовательности, расщепимые, вот здесь расщепимые и здесь расщепимые, вот под категорией, то там это функтор эквивалентности. Это очевидно. Потому что морфизмы, там один объект, а морфизмы те же самые. Это отображение из FG. Отображение из FG, ну, это будет морфизмы из FG, они образуют пучок в QC топологии. Вот. Значит, если я рассмотрю, значит, вот этот функтор индуцирует эквивалентность на подкатегориях. Ну, а теперь предположим, что у меня есть, so let's assume that now I have any extension. Okay, so I choose a covariant sieve, and for any object of the covariant sieve, well, I have a split extension restricted to this object. So I can construct, so for any y in this covariant sieve over x, I can construct an extension in the category of quasi-coherent sheaves on y. And so altogether, this gives me a locally given quasi-coherent sheaf, T tilde. And the category of locally given quasi-coherent sheaves is the same as the category of usual sheaves. So this has an interesting consequence that corollary is that H1 of x with coefficients in any quasi-coherent, sorry, is the same in, say, F PQC topology is the same as homology of G in Zariski topology. So for any G in the category of quasi-coherent sheaves on X. So really the content of this assertion is that any G torsor over X, which is locally trivial in this topology, is also locally trivial for the Zariski topology. For example, if X is affine, then it's trivial. And consequently, this is also equal to H1 for any topology which sits in between these two. For example, in Étale topology. So at least we know how to compute some homology groups. So fact, well, that I might have proof later, or at least split into several exercises, is that this is also true. Also true for HQ. This where Q is a natural number. Okay. So let me give another example. Where this interpretation of H1 as torsors is useful. So let's another example. Let C be a finite group. Finite abelian group. Well, then I can write, can look at cohomology, say étale cohomology of X, of some scheme X, with coefficients in the sheaf associated to this finite abelian group. For example, one way to define this sheaf, well, it's a sheafification of the presheaf of C-valued functions on open subsets of X. Another way is think of C as a finite scheme, group scheme. And then the sheaf represented by this group scheme is your C underlined. Okay? So, so we have an interpretation of this. This is a C torsors. Or which is the same. So this is kind of sheaf theoretic torsors. This is the same as we proved last time, because C is affine, well, geometric. Let's say C torsors. So that's what is a C torsor? It's a flat FPQC covers with an action of C such that the map from C to times Y to Y times Y, everything is over X, is an isomorphism. This map is given by the action. So, so I claim that this map, so why that? So I claim that any, so we proved that FPQC torsors so I claim that any C-tor, so we prove that this is true where torsors are considered in FPQC topology, locally trivial in FPQC topology. But I claim that if C is a discrete finite group, then this torsor is automatically trivial in étale topology. So what does it mean? It means that after some étale cover of X, it becomes trivial. What is the étale cover of X you need to take to trivialize this torsor? Y. Действительно, это отображение плоское, и слои у него C приведены, конечные. Поэтому оно этальное. А если взять это отображение, этот торсор поднять на Y, то этот изоморфизм как раз и будет означать, что он тривиальный.
Мы доказали, что в общем случае все торсоры тривиальны в плоской топологии, но в этом случае они не.
Да, да. Okay? So, in particular, if X is connected, then this can be interpreted as homomorphisms from pi 1 of x with coefficients in, well, with some base point x0 to C, right? So if this is if x is connected. Okay, so why that? What is a C torsor? So it's an étale map, finite étale map, with an action of C by automorphisms. What is a finite étale cover? It's a set with an action of this group. So that means that given a C torsor is equivalent to given a set S on which you have a simple transitive action of C and also a commuting action of pi 1. Right? Да. So you have, you can, there is an equivalence again between the category of C torsors and the category of following objects. A finite set with an action of the abelian group C and also with commuting action of pi 1. Isomorphism classes of such objects are in one-to-one correspondence with homomorphisms. Namely, you pick any point of S, so then this point identifies S with C, and then action of pi 1 defines a homomorphism from pi 1 to C. It's important here that C is commutative. Otherwise, it will depend on the choice of. So you can also, if C is non-commutative, you can still interpret C torsors as homomorphism from pi 1 to C up to conjugation. Very good. So let's see if we have, and that's also the same as flat topology. So here is another example, maybe 2 minutes or 5 minutes. I will take 5 minutes. So let's take, let me explain, let me do some more interesting computations. So, Kummer's theory. Okay, so let's consider the group scheme GM. That's the multiplicative group. And I think of this as a group scheme over Z, over spectrum of Z. And for an integer n, let's consider homomorphism from this group scheme to itself that takes Z to the nth power. So, well, that's a homomorphism of groups, and it has the kernel in the category of group schemes. So it's the fiber product, right? It's you have one here, and you take the fiber product. That's called, that's going to be a finite group schemes, which is called mu n. So it's points with values in any field has just roots of unity of order n in this field. So, so this morphism of group schemes defines an underlying, well, a morphism of corresponding sheaves represented by these group schemes. So what are these sheaves explicitly? Well, GM, so this is sequence, exact sequence in the category of sheaves, say, I can take sheaves in all schemes in FPQC topology. So what is this sheaf? So values of these sheaves at X are just invertible functions. By definition, these are homomorphisms from, well, these are maps from X to GM. And what are mu n? X-valued points of mu n. These are functions, or X star, such that f to the nth power is equal to 1. So if X is connected, then they're all roots of unity. Oh, they're roots of unity kind of anyway, but don't have. So theorem, this is an easy theorem, but it's very, very important because it's hard to all computations that we will make in this course. So, let's give a name to this sequence. I claim that this sequence is exact in so exactness is, I'll put 0 here. I didn't write that it's exact. Is exact in category of sheaves on all schemes in FPQC topology. And this is part A, and part B is that so it's exact even in weaker topology. So I take sheaves in over Z. So it's going to be exact in a weaker topology, provided that I invert, that I look at schemes where n is inverted. So I look at schemes over Z with n inverse adjoint, right? That's a subring of Q for a type topology. Right? Now let me finish by proving this. So proof, well, proof is, I will prove B. Proof of A is easier, you'll see. So what do you need to prove for B? So the point is that it suffices to prove that, well, exactness, the fact that this sequence is left exact is automatic. Just it's exact even, it's left exact as sequence of pre-sheaves. What is non-trivial is subjectivity of the last map. So what does it mean? It means that, so this map here is induced by, well, it's given by the raising, it takes a function f, right, to its nth power. And the claim is that a tau locally, provided that n is invertible in the ring of global functions on X, a tau locally we can extract nth root of f. That's really the statement of the theorem. And so this follows from the fact that the map, so we consider GM, and now this is GM is a group scheme over Z. Now I best change it to spec Z with n adjoint, n inverse adjoint. Z with n inverse adjoint. So that's, again, so Z goes to Z to the nth power. So this is the map that obtained from this sequence by best change. And I claim that this is an étale cover. Is an étal cover. Right? So why it's an étal cover? First of all, it's flat, because even this map is flat, right? What are functions on this space? It's a free module or functions here. These are Laurent polynomials in, if you identify functions here with Laurent polynomials in Z, then this is identified with Laurent polynomials in Z to the nth power. And this is a free, one is the free module over the other, with basis 1, Z, Z squared, and so on. So it's flat, it's surjective on points, and the key point is that it's étal once you invert n. Well, to check that it's étal, it suffices to check that its differential is invertible. But the differential is n times z to the n minus 1. Z is invertible, and n is invertible. So we are done. And now, so given this, how you check that this is again, that this is exact. So you, if you have a morphism from some scheme X to this guy, so that means that a section of, you have a scheme X over this, together with a section of GM underlined over X. This all together gives me a morphism from X to this product. And the goal is to show that there exists a cover, an étal cover, such that this composition lifts here. And you can take for you the fiber product. Okay? I will stop here, and next time we will derive some corollaries from this. Какое рассуждение? Самое последнее. Ну, давайте посмотрим, что нам надо доказать вот здесь. Мне надо доказать, что вот это отображение суръективно. Давайте посмотрим, что это означает. Значит, вот у меня есть какое-то сечение GM на x. Ну, что такое сечение GM на x? Это означает просто обратимая функция на x. Ну, само x еще над z, над этой штукой. Поэтому, ну, обратимая функция задает мне вот такое отображение. Значит, это вот сечение GM от x. Этот пучок еще называется со звездочкой просто. Можно со звездочкой. Вот. Да, там уже написано. Значит, и что мне надо доказать? Что локально по x в этальной топологии вот это сечение, оно поднимается до, вот это отображение, поднимается до вот такого. Ну а что означает, что локально в этальной топологии? Это означает, что существует покрытие x в этальной топологии. Такое, что если я ограничу вот это отображение на U, а что означает, что ограничу? Ну, возьму композицию просто. То вот это вот новое отображение, вот эта композиция, она будет уже подниматься до такого. То есть вот существует стрелка, которая делает эту диаграмму коммутативной. Значит, итак, для каждого x и такого отображения мне нужно придумать U, которое будет этальным покрытием. Но в качестве U нужно взять расслоенное произведение x и gm. Ну, на gm. Ну, в смысле, что здесь действие, ну, вот это отображение, оно вот задается такой формулой. Абсолютно верно. Ну, а в плоской топологии, значит, ничего не нужно.
Я говорю о минус первой, что
да.
Хорошо. Я просто пропадаю, себя не слышу.
Is H1 F in our previous series? Are these cohomology groups in the small tel site or in the large tel site?
So let's see. So are you What is the theorem? Let's see.
So of course, you work in this large house.
Yes, and what is the theorem that you?
And then torsors, we did have smaller tiles find, or not?
Well, so G. So here it doesn't matter. You can take any. So for this corollary, you can take any. For Kummer theory, so far we didn't talk about cohomology. So, and we'll talk about cohomology next time, but so here I take large étale site.
Yes, but the sequence is still exact to the small étale site, right?
It's automatic, right? So if you have if you have any sequence of sheaves on a big étale site, if you restrict it to small étale site, by definition, it's still exact.
And because the covers are.
Yes, covers are generated by.
So there are more objects,
But
also,
yeah,
so the
yeah.
sheaves in the big étale site are like you have for any scheme you have factorially to give a sheaf in small étale site.
Yes, you just see. So the category of objects of big étale site is of small étale site is a subcategory of the category of objects of small étale site. So you can restrict pre-sheaves. But restriction of a sheaf is going to be a sheaf.
I also have trouble, so I looked up at the stats project and I have trouble figuring out whether our definition of étale topology is equivalent to their definition. So
Of which topology?
of étale topology.
Topology.
So what they do is they say that the covering is standard étale if it's an étale covering and all schemes are defined UI. And then they prove that any étale covering can be refined by standard étale covering, and they only allow sieves which are generated by standard étale covers. So it seems that they have less covering sieves.
Well, if the cover can be refined by any étale cover can be refined by standard étale covers, so the sieve generated, it means sieves. Well, it means that the sieves, cover and sieves are the same, right?
No, it seems that we discard sieves that are generated by covers that are too large.
That are too large.
We discard.
No, so what does it mean that, so suppose you have a cover that, so if one sieve contains the other, and smaller is a covering sieve, then larger is also a covering sieve,
Why?
by definition.
We don't have.
It's called locality.
Oh. You take any cover, you generate
yeah.
a sieve, and you check that the
Yes,
cover
yes,
is
yes,
equal to the
yes.
cover.
Mm-hmm.